Okay, so also good morning, everyone, from my side, and I welcome you to the GeoDict Innovation Conference in 2025. It's a pleasure to have you all here today, and now we dive into the latest advancements in GeoDict. And throughout this presentation, I will guide you through these innovations and show you how GeoDict can help streamline workflows, optimize material design, and improve efficiency across industries. So before we get started, let me introduce myself. My name is Martina Hümbert, and I'm Deputy Team Leader of Business Development at Mark to Market. My background is in material science. I did my PhD here at the University in Kaiserslautern, focusing on composites, and I joined Mark to Market in 2019. And I'm in my current position since 2023. And today I'm really excited to share with you the latest improvements in GeoDict 2025 and how they can benefit your research and development efforts. GeoDict brings a range of enhancements designed to boost work efficiency and to improve simulation accuracy. The key areas of innovation this year include general improvements to performance and usability, advancements in batteries, fuel cells, and electrolyzers, improvements in nonwovens, composites, and filtration simulations, and new features in digital rock physics to improve the permeability and heterogeneity modeling. One major workflow enhancement is the improved job system, which allows users to queue multiple simulations locally or on a remote server. This feature eliminates the need for scripting thanks to its graphical user interface, and it enables the seamless integration into research and industrial workflows. This improvement is particularly useful for teams working together, where optimizing research users can save significant time and effort. And GeoDict 2025 introduces several enhancements to the job system, providing greater control and visibility. You can now monitor jobs of all users, you can download data from completed simulations, you can prioritize jobs by rearranging the job queue, and you can terminate or delete outdated jobs to free up the system resources. And these features ensure a smoother workflow, helping teams to manage computational tasks more effectively while making the best use of your available computing power. So talking about efficiency, one of our key goals is to provide users with a fast and easy access to the information they need. And that's why GeoDict includes a content-specific help directly within its dialogues. By simply clicking on the Help button, users are taken to the relevant section of our searchable online user guide. And this means no more searching through lengthy menus, just instant access to the explanations and settings for the exact feature you're working with. This ensures a smooth workflow, minimizes your downtime, and helps users to get most out of GeoDict, because we at Mark to Market believe that excellent support is in our DNA. So now let's talk about some key improvements in the interaction between user and software. We've made sure that detailed statistics are right at your fingertips. Just hover over the tooltip and you'll get all the insights you need. Another small but incredibly useful change, you can now copy tooltips directly via the context menu with a simple right click. No more manually transferring data, just grab the information instantly. And we've also enhanced how you can interact with the graphs in the result viewer. You can now get precise plot values simply by hovering your mouse over a point. No need to guess or approximate. And to make navigation even more intuitive, zooming is now fully integrated with mouse controls. Whether you are exploring trends or examining fine details, this makes analysis much more fluid. The key takeaway, access to important information in just a second. So far, we focused on improving how users interact with the software and data. But now let's move to a breakthrough for your data acquisition, converting 2D images into full 3D microstructures. One of the biggest challenges in digital material analysis is the transitioning from 2D imaging to accurate 3D representations. 2D images, whether from a thin section, an SEM scan, or other imaging techniques, are quick and cost-effective to obtain. However, they only provide a partial view of the materials through microstructure. With GeoDict, we're making this transition seamless. By leveraging advanced reconstruction techniques, we can generate realistic 3D models from these 2D inputs. So now let's take this concept a step further, using GeoDict's granular digital twin app. By using a 2D SEM image as input, we can generate a fully optimized 3D model that closely matches the real-world material properties. This process includes refining parameters like pore and grain size, chord length, and surface areas, and then validating the final structure against reference data. And as you can see here at the example of an SOFC cathode, the weighted average error across key metrics is impressively low, ensuring that our digital twin is both precise and reliable. So as we progress through this presentation, you will see how GeoDict 2025 addresses key industry challenges in multiple domains. And now we will start with batteries, fuel cells, and electrolyzers. So let's shift gears and talk about something we all want, the battery of our dreams. Imagine setting off on a road trip without ever worrying about your battery running out. With this next generation battery, you get the freedom to travel longer distances without constantly searching for a charging station. And when you do stop, charging is no longer a hassle. By the time you grab the coffee and stretch your legs, your battery is fully charged. Fast charging like this makes long trips effortless and stress-free. And most importantly, this battery is designed for absolute safety. No overheating, no fire risk, just reliable performance under all conditions. With advanced simulations optimizing its design, you can drive with total confidence. So we want a battery that lasts long, charges incredibly fast, and it's built for safety. But what happens when we push the limits further? That's where we have to talk about one of the biggest challenges in battery technology, degradation. And one of the most critical risks, lithium plating, where lithium deposits on the anode. This reduces battery capacity over time and worse, increases the risk of a short circuit and failure. With GeoDict, we can simulate and predict these risks before they happen. We analyze plating potential at the active material surfaces and identify high-risk areas where lithium deposition is likely to occur. In this example, the potential for lithium plating at a charge rate of 3C is obviously highest at the separator. These insights help to optimize charging strategies and material designs, ensuring that fast charging doesn't come at the cost of battery health and safety. Beyond lithium plating, another major challenge in battery performance is heat generation. Every battery produces heat during operation, but excessive heat can reduce efficiency, damage components, and even lead to failure. GeoDict 2025 allows us to visualize and analyze heat distribution inside the battery cell during charging and discharging. In this example, we have a graphite NMC battery charged from 3.5 volt to 4.1 volt in 15 minutes. The top right graph shows the cell potential over the charging period, while the bottom right visualization highlights where heat is generated inside the cell. For example, you can see that the heat production in the electrolyte in the graph remains relatively constant, but the volume field relieves localized hotspots, particularly near the separator where many ions pass through narrow pore necks. By pinpointing these thermal effects, GeoDict helps us design safer and more efficient batteries, reducing energy loss and preventing potential failure of the battery. So we tackle fast charging, lithium plating, and heat management, three critical challenges in battery technology. But what if we take things a step further and rethink the very structure of the battery itself? That brings us to one of the most exciting advancements in next-generation energy storage, all-solid-state batteries, which promise higher energy density, improved safety, and longer lifetimes compared to traditional lithium-ion batteries. But designing these advanced cathodes isn't simple. It requires precise control over the microstructure to balance conductivity, porosity, and mechanical stability. With our new ASSB cathode generator, you can digitally create and optimize realistic cathode structures by combining high-resolution 3D imaging, statistical modeling, and simulation. You help accelerate the development of next-generation batteries, bringing you closer to safer, more powerful, and more efficient energy storage solutions. And that, of course, would not be possible without all our partners in the Delphine project in which we are working on this topic. So as we transition toward a sustainable future, the challenge is to replace fossil fuels with clean energy alternatives. We already talked about batteries, and now we look at the second part of the puzzle, fuel cells. And when you say fuel cells, you also have to say electrolyzers. Hydrogen is a key player in the clean energy landscape. It is needed for oil refining, fertilizers, and steel production. Today, the very biggest part of hydrogen comes from fossil fuels. But when we want to move into a greener future, we need to get this hydrogen from water electrolyzers and to replace fossil fuels by fuel cells. To make that happen, production of green hydrogen must be efficient and cost-effective, and that's where GeoDict steps in. We help you in designing efficient water electrolyzers for green hydrogen production, in optimizing electrode and catalyst structures, and in simulating gas transport and reaction kinetics. In a fuel cell, the efficiency of energy conversion depends on how well different components interact. Just like a well-organized city with smooth transportation, a fuel cell needs an efficient transport system for electrons, oxygen, and water. Everything must travel from the bipolar plate to the catalyst efficiently. Oxygen must diffuse into the catalyst layer through interconnected pores, and the water produced in the reaction must be transported out of the reaction area to prevent flooding. GeoDict 2025 helps simulate and optimize these transport pathways, ensuring that fuel cells operate at peak efficiency. Under operation, not only the interaction of the different components is important, but also mechanical deformations occurring in the porous transport layer, short PTL. So first, let's have a look at those cans. Can they obtain the same amount of liquid? No, definitely not. And the same is true for the PTL. So what can you do? You can perform a mechanical deformation simulation with GeoDict to get realistic microstructural input parameters for your performance model. And why do you need those compressed microstructures? During operation, components of the electrolyzers and fuel cells undergo compression. And micro-CT scans, as well as many traditional experimental methods, can only capture the material state before compression, limiting accuracy and performance models. With GeoDict 2025, we can simulate material compression to obtain realistic deformed geometries. We provide accurate input parameters for performance simulations, and we improve predictions of fuel cells and electrolyzers efficiency. And these advancements ensure that real-world effects are accounted for in simulation models. As we move forward, we will now focus on material science applications, particularly in nonwovens and composites. These materials play a key role in many areas, such as personal care, insulation, or aviation, and GeoDict 2025 introduces new tools to enhance their design and performance. We just talked about the importance of the compression of the PTL for a fuel cell. The same applies for porous materials, such as foams and nonwovens, that also undergo deformations. Understanding these deformations is crucial for optimizing their mechanical properties. And GeoDict 2025 introduces a new resampling method that improves deformation accuracy by accounting for volume changes, and an improved algorithm for maintaining volume fraction in deformed geometries. These enhancements allow for a more precise simulation of material behavior under different loading conditions. And just have a look at these. I think that these deformations look really amazing. So, as I already said, fibrous materials are used in a variety of applications. Fiber length is then a key parameter that significantly impacts the performance and properties of many materials and products. In the case of nonwovens, fiber length determines crucial properties like permeability, capillary pressure curves, and mechanical performance. In hygiene and medical products, it impacts softness and strength, while in construction, it contributes to insulation and durability. On the other hand, for composites like injection molded or SMC parts, fiber length and orientation play a pivotal role in the manufacturing process and design aim. Longer fibers often enhance the mechanical performance of composites, providing better strength and stiffness. Meanwhile, shorter fibers may be more suitable for intricate designs or faster production cycles. And understanding and optimizing fiber length is essential to achieve the desired properties and performance of products. With FiberFind AI and GeoDict AI, we already enabled you to analyze CT scans of your nonwoven or composite and get all the statistical data you need. Now those modules also include multi-channel segmentation, allowing users to distinguish different types of fibers in a single scan. The neural network can be trained to differentiate between round, trilobal, and hollow fibers, as you can see on these 3 images in the center. And this capability streamlines the analysis of fiber-based materials, such as textiles, nonwovens, improving design and manufacturing processes. And while in FiberFind AI, you can use pre-trained neural networks that we ship with GeoDict, you can train your own networks in GeoDict AI. But how does that work? Users can create large data sets of slightly different structures as training data directly in GeoDict, for example in FiberGeo. Neural networks can be trained using these artificial structures, being perfect for your material. And once trained, these networks can be applied to real-world scans to automate segmentation and material analysis. This feature allows everyone to train AI models, making it easier to apply machine learning in material science. Now we turn to advancements in filtration technology. Filtration is crucial for clean air, water, and industrial processes, and GeoDict 2025 introduces several features to improve the design of filtration media. Imagine a world where air pollution is no longer a threat, where every city enjoys clean and breathable air. With GeoDict, we can design and optimize advanced filtration systems that efficiently remove harmful particles and gases. So air pollution, as I said, is a major global challenge affecting human health and the environment. And filtration technologies play a vital role in mitigating air pollution, and GeoDict helps in designing more effective filter media. Electrostatically charged filters offer high efficiency at low pressure drops, making them ideal for air filtration. GeoDict 2025 now includes improved electrostatic simulations so that one can model different charge configurations on fibers and simulate the interaction of charged particles with filter media. And we successfully included dielectrophoresis and electrostatic decay functionalities. And of course, we keep working on further validation of this simulation with experimental data. In the filtration industry, adsorption-based processes to remove contaminants and odors are present in a wide variety of applications in daily life. In most of the applications, materials with large internal submicron surfaces like activated carbon are used. For example, in agriculture, these filters protect farmers against fertilizers and pesticides, whereas our drinking water or wastewater also benefit from these materials. And one of the major challenges in adsorption-based filtration is predicting when a filter becomes saturated, so when it's full. And GeoDict 2025 introduces breakthrough curve calculation to predict when a filter will reach its absorption limit. You can see that curve and the simulation in this video, and Langmuir Toth absorption isotherms for accurate modeling of contaminant capture. And these tools allow engineers to optimize filter design for maximum efficiency and lifespan. So as we move forward to the final section, we will now discuss innovations in carbon capture and digital rock physics, which are essential for tackling climate change and optimizing resource extraction. We all know that carbon dioxide emissions are a major driver for climate change. Reducing emissions is critical, but what about the CO2 that is already in the atmosphere? That's where carbon capture comes in. One of the most effective ways to remove CO2 is capturing it directly at the industrial sources, like power plants, before it even enters the atmosphere. Using advanced adsorption technologies, we can efficiently trap and store CO2, turning a major problem into an opportunity for cleaner energy and more sustainable future. And GeoDict 2025 enables the simulation of these processes, helping researchers design better carbon capture solutions. In GeoDict 2025, we are taking precision to the next level with subvoxel resolution in the Lear solver. What does this mean in practice? Instead of being constrained by voxel size, the solver now intelligently refines the grid, ensuring even the smallest flow pathways are properly captured. This translates to a larger section that can be analyzed, a high accuracy in simulations, better predictions for permeability, and ultimately more reliable results for industries relying on digital rock analysis. So now that we've enhanced our ability to simulate flow in narrow channels with subvoxel resolution, let's take a step back and look at the bigger picture. Because not all rocks are uniform, in reality, geological formations are often highly heterogeneous. Which brings us to our next challenge. How do we accurately model materials that vary so much in structure? In an ideal world, we'd analyze entire rock formations at the microscopic level. But in reality, that's just not feasible. Instead, we need to bridge the gap between small-scale scans and large-scale reservoir or material behavior. This is where upscaling comes into play. By capturing key properties from high-resolution micro-CT scans and applying them to larger samples, we can already predict overall permeability with confidence. Essentially, we are translating detailed, localized data into a form that makes sense at a much larger scale, giving us more accurate representation of a real-world performance. And one powerful method for understanding porous materials is mercury injection capillary pressure, or MICP. It tells us how pore structures behave under different pressure conditions, giving insights into flow properties, storage capacity, and connectivity. But again, we face the challenge of scale. A single micro-CT scan can only capture a small portion of a material, and different regions can behave very differently. That's why we're introducing MICP upscaling. By systematically analyzing multiple micro-CT samples and integrating them into a whole core model, we can generate upscaled capillary pressure curves that represent the true variability of the material. With these advancements, we're making sure that no matter the scale, our insights remain precise and reliable. So innovation is a journey and not a destination. And while we've introduced powerful new capabilities in GeoDict 2025, we know that the real magic happens when these tools are put into practice. And that's why we're inviting you to dive deeper into our breakout sessions. And beyond that, we are continuously refining our technologies. Your feedback and real-world challenges help shape the next generation of GeoDict, ensuring that we keep delivering solutions that matter. And so let's keep the conversation going, explore new possibilities together, and drive the future of digital material design, digital material research. Because the best innovation is always just ahead. So thank you very much.